This is the lecture on secondary biological treatment. Our learning objectives for this lecture are to apply your knowledge of material and mass balance, to derive the equation used to model biomass concentrations and the removal of COD in suspended growth biological secondary treatment processes, to calculate microbial yield and oxygen requirements for biological wastewater treatment processes based on the principles of stoichiometry, to calculate oxygen demand and determine flow rate and power requirements for aerators, to design an activated sludge process by choosing appropriate values for the aeration period, organic loading, food to microorganism ratio, suspended solids and bCOD removal efficiencies, sludge age, and return activated sludge rate, and to calculate sludge production based on the observed yield or wastewater characteristics. So again, in our typical biological wastewater treatment system, for this lecture, we're now focusing on this process right here, the secondary treatment processes. The objectives of biological treatment for domestic wastewater is to oxidize biodegradable constituents and convert them into acceptable end products. For example, oxidizing carbonaceous compounds that are present in the wastewater and converting them into CO2, which is released back into the atmosphere. We're also interested in incorporating suspended and non-settlable colloidal solids into biological flocks, which can be settled out into the sludge. For industrial wastewater treatment, the objectives are to remove or reduce the concentration of organic or inorganic contaminants that may be present in the wastewater, and in some cases, pre-treatment, which is used applied to the wastewater prior to discharging to a municipal collection system. This will prevent any organic or inorganic compounds that may be toxic to the centralized wastewater treatment processes, prevent those from inhibiting the treatment processes downstream. So this is usually part of the National Discharge Pollution Elimination System, the NIPD's permit system. Requirements is that municipal wastewater treatment authorities, wastewater collection and treatment authorities may require industrial wastewater dischargers to apply pre-treatment before they discharge their wastewater into the municipal collection system. So again, getting back to municipal wastewater treatment, which is mostly domestic wastewater, we are talking about the microbial oxidation of organic matter in sewage. Unlike water treatment, where we're mostly using physical chemical treatment processes, for wastewater treatment, we rely mostly on biological treatment processes. So essentially, we're letting the microbes do the work for us. All right, microorganisms are used to oxidize. They're converting the dissolved and particulate compounds into simple end products and additional biomass. All right, so we have kind of a generic stoichiometry for this process that's happening, where we've got organic compounds in the wastewater, which are being converted to microbial biomass and CO2 in the presence of dissolved oxygen. So the dissolved oxygen is used for balancing the redox reaction that takes place. It's the terminal electron acceptor for the microbial processes that are being used to break down these organic compounds. And so therefore, in this type of system, which is aerobic, we are purposefully pumping air or oxygen into the wastewater so that the microorganisms have an unlimited supply of dissolved oxygen in order to complete this reaction. All right, so the aeration of wastewater, this has been studied for more than 100 years. And in 1914, this process of aerating the wastewater to treat it was named activated sludge. And that was the reason for that name was because of the microbes that were in the wastewater that became activated and helped stabilize the organic matter present in that wastewater. So the components in the activated sludge treatment system include a reactor or an aeration tank where the microorganisms are kept in suspension. So this is basically like our growth chamber for the microorganisms, a liquid solid separation reactor, it's usually a clarifier, and a recycle system that returns a portion of the solids back to the reactor. So you can see here in this figure below, we've got our primary clarifier, which is used just mostly to remove some of the larger biological solids that are present in the sewage before activated sludge. And then after primary treatment, we go into the activated sludge system, which again consists of the aeration tank, the secondary clarifier, which settles out the microbial biomass that grows in the aeration tank, and then a return line that returns a portion of those microorganisms back to the beginning of the system. And then a portion of those microorganisms will be wasted. So therefore, the hydraulic retention time through this system, or the amount of time that water spends passing through the system, is lower than the solids retention time, or the average amount of time that a microbial cell spends in the system, because we're purposefully settling out those microbial cells and returning them back to the beginning where they can continue doing their work of breaking down that organic matter. All right, so some design considerations for activated sludge. We've got different types of process configurations that have been developed throughout the years. So we would choose which process configuration is the most suitable for our particular needs. We've got the oxygen requirements, the oxygen transfer rate, the solids retention time, which is also called the sludge age. We've got the volumetric loading rate, the food to microorganism ratio, and the sludge production rate. So these are some of the design considerations, and we're going to go into each of these in detail. All right, so first let's start talking about process configurations. So perhaps the most typical process configuration is what you see right here in the figure, where again, you've got the primary clarification followed by aeration. And with this symbol right here, it's intended to indicate that this is assumed to be a completely mixed system or close to it. So we're mixing the wastewater in the aeration tank so that essentially this tank is very well mixed. From there, the wastewater gets discharged to secondary clarifier. At this point, it's got lots of microorganisms that have grown inside the aeration tank. In the secondary clarifier, that microbial biomass is allowed to settle down to the bottom, and the clarified liquid effluent is going to be discharged as secondary treated wastewater. The biomass that settles out will be conveyed with a pipeline. A portion of that will be returned back to the beginning of the aeration tank, and a portion of it will be wasted as waste activated sludge. All right, so this is the most standard conventional configuration for activated sludge. We've also might have some systems where the aeration tank is designed in a different way to try to achieve more close to a plug flow regimen. So instead of complete mix, we have a little bit more like a plug flow reactor. But other than that, the process is essentially the same. The calculations, however, will be different because of the nature of the flow and the hydraulics. Sequencing batch reactors might be used in some small scale applications. So the same principles are true for the activated sludge process. However, the flow regimen is different. So we have a single tank, we're filling it up with sewage. Then after it's full, we'd stop pumping into this tank. We would probably start pumping the sewage into a different parallel tank. And while that's happening, we would be aerating the sewage in this first tank. After the aeration period, we would stop, let the wastewater settle down to the bottom, or let the biomass in the wastewater that has grown, let that settle down to the bottom, and then decant, essentially skim off the cleaner liquid that's present at the top of the tank, and the heavier biomass a portion of which would remain for the next time the tank is filled up. So you're achieving the same thing just with a different type of flow regimen. Another process configuration that's been developed over the years is the one you see here. It includes a series of internal recycles and switching back and forth between anoxic and aerobic reactors in sequence. The purpose of this process configuration is to achieve more efficient removal of nitrogen compounds in particular. nutrients in general. So with nitrogen cycle, you know that first the wastewater comes in with nitrogen mostly in the form of ammonia. That ammonia will be oxidized in the aerobic reactor. It'll be oxidized to nitrate. That nitrate then can be converted to nitrogen gas in a process called denitrification. However, denitrification requires anaerobic or anoxic conditions, and it also requires the microorganisms to have a carbon source. So if we were to just have anoxic, aerobic in series, by the time the nitrate is discharged to, let's say, the second anoxic tank where it can undergo denitrification, the carbon concentration is going to be quite low because the wastewater will have already been oxidized by the heterotrophic microorganisms in the first aerobic chamber. So you're going to have very low COD concentrations, and the denitrification would not work unless we added back a carbon source. In some wastewater treatment systems, they actually add methanol or a different carbon source into the anoxic reactor in order to achieve denitrification. However, in other systems, they utilize an internal recycle of the mixed liquor. Mixed liquor is what we refer to as the microbial biomass that's growing in the aeration chamber. So they're internally recycling that from the aerobic chamber back to the first anoxic chamber, and that allows the denitrification to take place because we've already got nitrate, which has been produced in this first aerobic chamber, and we're bringing that nitrate back to the first anoxic chamber where we've got plenty of carbon because that's receiving the raw influent. So this process configuration is essentially the same as the first one, with the difference that we've got this aerobic anaerobic sequence, which helps achieve better nutrient reduction throughout the system. We've also got another major modification of the activated sludge process that has become popular over the past couple decades. It's called the membrane bioreactor system. So this system, rather than separating out the biomass using clarification, the biomass is separated from the liquid effluent, or in this case, we would call it the permeate. It's separated using membranes. So we have submerged membranes that essentially filter out the water after the aeration process. And what's retained on those filters or those membranes is going to be internally recycled. A portion of it will be wasted, and what passes through those membranes, called the permeate, will be discharged as secondary treated wastewater. The advantage of this process is that not only do you get separation of the biomass from the liquid effluent, but you also get a much greater pathogen reduction in these systems. So you can utilize this technology in a system that would achieve wastewater reuse. So to model suspended growth treatment processes, we can use a few basic assumptions with a mass balance approach. So the first assumption is that we'll treat the aeration basin as if it were a continuously mixed flow-through reactor. We'll also assume that the influent has a very low concentration of active biomass relative to the aeration basin. So when we model the biomass, which we use the variable X for biomass, when we model the biomass coming into the system, we can assume that that's negligible compared to what's growing within the system, so that it will be equal to 0. We'll assume that biodegradation, or the conversion of the carbon compounds, we'll assume that that only occurs in the aeration basin. And we're also going to assume Minod kinetics with single limiting soluble substrate. And I'll get into detail in a couple minutes on what that means. The key concept for suspended growth treatment processes for biological systems, the key concept is that SRT is greater than HRT, and that's due to the sludge recycling that takes place. So SRT being the solids retention time and HRT being the hydraulic retention time. So the long SRT makes for conditions that produce a low effluent substrate concentration because you've got very efficient biodegradation taking place, leading to a low COD or BOD concentration in the effluent. The low hydraulic retention time leads to us being able to design a smaller reactor volume, which saves on costs, saves on land space. It's a high throughput system with an economy of scale for treating wastewater. All right, so let's talk a little bit about microbial growth and the fundamentals of microbial growth. So if we were to put wastewater in a jar for a period of time and let the microorganisms degrade the organic matter in the presence of oxygen. So we have wastewater in a jar. Let's say that we're pumping oxygen into that jar. There's going to be a few distinct phases of growth that take place. The first phase is called the lag phase. So this is where the microorganisms are kind of getting used to the substrate. They're getting used to the conditions. At a molecular scale, this means that the microbes are making enzymes to break down the compounds that are in the wastewater. The growth is somewhat slow during this phase. The exponential growth phase happens after lag phase, and this is when the cells are in their healthiest state. They've got an abundance of food, they've got an abundance of oxygen, and they're growing at a rate that is exponential. So the change in the concentration of biomass with respect to the change in time is equal to mu times x, where mu is the growth rate. If we were to derive this equation, we would get the form x of t is equal to x0 times e to the mu t. And so you can see that that is an exponential equation that'll give you a growth curve that looks like you see right here in the exponential growth phase. All right, so the biomass concentration at time t is equal to the biomass concentration at time 0 times e to the mu times t, where mu is the growth rate and t is the time. After the growth phase, there's a stationary phase, and that stationary phase is a time when the microbes start to feel stress. They're starting to run out of the food source, so the cells switch over into kind of a starvation mode. The growth rate is approximately equal to the death rate, so what you have is just kind of a flat concentration curve with respect to time. And we use mu for the growth rate, we use B for the death rate, for the decay rate of the microorganisms. Then after the stationary phase, we have the death phase where there's a depletion of nutrients, there's an increase in toxins, and the change in concentration with respect to the change of time is equal to negative B times X. So Minod growth kinetics refers to the microbial growth rates that occur with consideration of the effect of substrate concentration. So when we talk about substrate, what I mean is the food, really, the COD, the BOD, the organic matter. All right. The Minod experiment is where you perform a series of growth experiments at varying substrate concentrations. So let's say you have microbes in a jar with varying concentrations of COD, and you're measuring their growth rate based on the exponential growth phase in each experiment. And then you're going to plot the growth rate for each of those experiments with respect to the substrate concentration that was applied. So for lower COD concentrations or lower substrate concentrations, you're going to have a slower growth rate. For higher substrate concentrations, you're going to have a higher growth rate. Until you get to a point where the substrate concentration is so high that it really doesn't matter anymore, the growth rate is going to stay pretty consistent. All right, so the curve looks like this. This is an empirical curve. It's an empirical equation. You've got, again, the growth rate is maxing out at a value of mu max, or in some cases this is used, the notation is used mu hat, and that occurs as the substrate concentration approaches infinity. If you take that mu max value, divide it by 2, and you find the corresponding substrate concentration on the curve from the data, what you get is a value that's known as K sub S, which is the half saturation rate constant. It's the concentration of substrate that produces a growth rate that's half the maximum specific growth rate. All right, so this empirical equation, which is called the Minod Equation, looks like this. It's mu is equal to mu hat, which is mu max, multiplied by S, which is the substrate concentration, divided by the half saturation rate constant plus the substrate concentration. All right, so that is the Minod equation, and we're going to be seeing that a little bit later when we work through the modeling equations for activated sludge. All right, so correlated with microbial growth is the utilization of substrate, because as the microbes are growing, as they're metabolizing, they're degrading the substrate. All right, so we can define the substrate utilization rate as R sub SU. And that's equal to, it's defined by this equation, it's equal to K times X times S divided by K sub S plus S. K sub S being the half saturation rate constant, according to Minod kinetics, S being the substrate concentration, and X being the biomass concentration in the reactor. K in this case is the maximum specific substrate utilization rate. So it's equal to the maximum specific growth rate divided by the yield. And R sub G is the bacteria growth rate from substrate utilization. It's the maximum specific growth times X times S divided by K sub S plus S. All right, so you've got these series of equations that define substrate utilization. We're going to come back to that in a second. So the net biomass growth rate, R sub X, is equal to the yield times the substrate utilization rate minus the death rate times the concentration. So basically, it's the microbial yield multiplied by how fast they're utilizing the substrate. And then we subtract from that how fast they're dying off in the system to get the net biomass growth rate. So if we were in the stationary phase, the net biomass growth rate might be 0. If we were in the death phase, this term might be negligible. You'd have negligible substrate utilization, negligible yield, and you would be controlled by the death rate. If we were in the exponential phase, then this death term right here, this decay term right here would be very small compared to the yield and the substrate utilization. So you can see here what we're calculating is the net biomass growth. All right, and based on what we know about the substrate utilization rate, this is also equal to Y times KXS divided by K sub S plus S minus B times X. If we divide both sides of this equation by X, it gives us what's called the specific growth rate. So that's mu, and it's also equal to Rx divided by X. It's basically the growth rate normalized by the concentration of biomass in the system. All right, so then the rest of this here is just algebra. Y R sub SU divided by X minus B, and it's also equal to Y KS divided by this maximum, the half saturation rate constant plus S minus B. All right, again, we're going to come back to those equations. So again, modeling suspended growth treatment processes. So with that preliminary knowledge and kind of definition, mathematical definitions for biomass growth and substrate utilization rates, the next step to model suspended growth treatment processes is to utilize a mass balance approach. So we've got several different cases based on our process configuration, as we mentioned before. This one right here, case 1, is the most traditional, most conventional configuration where sludge is being wasted from the return line. So we're going to call this case 1, and we're going to do some examples using this case. We can also have case 2, where instead of wasting happening at the return line, the wasting is happening from the aeration tank or from the effluent of the aeration tank as shown here. So the mass balance in case 2 would be slightly different from the mass balance in case 1. Why? Because what's leaving the system as X here is equal, in case 2, it's equal to the mixed liquor concentration X in the aeration tank. But in case 1, what's leaving the system is X sub R, which is higher than the concentration in the aeration tank, because it's already gone through the clarifier, further concentrating those biomass, the biomass in the sludge. So you're going to have a higher concentration leaving the system here, a lower concentration leaving the system here, and that is going to make the mass balance equations slightly different between these two cases. So we're going to do some exercises using case 1 and to demonstrate the process, but you should be able to also apply the same approach using your knowledge of material and mass balance. You should be able to apply it to case 2 to solve problems related to activated sludge. This is our mass balance, and you can see it drew the boundary here in dotted lines. So to set up the mass balance, we have to calculate the accumulation. This is equal to the inflow, what's coming into the system, minus the outflow, what's leaving the system, plus the net growth. So what's growing inside the system. And under steady state conditions, we usually assume that this is equal to 0. All right, so what's coming into the system? That is, in terms of volatile suspended solids, our x variable, Q times x naught. What's leaving the system is QWXR. This is the flow rate of waste sludge and the concentration of biomass within that waste sludge line, so QWXR. And also we have leaving in the liquid effluent QE times XE. Plus the net growth. So net growth here can be represented by the growth rate, R sub x times V, the volume of the aeration basin where the growth is occurring. All right, so some things that we can assume, since basically what we have is a small concentration of volatile suspended solids in the actual wastewater, so there are some microbes in the wastewater that's entering the system, but relative to what grows inside the aeration tank, the concentration of volatile suspended solids in the influent is relatively low. So we can ignore that for the purposes of this mass balance and treat it as negligible relative to the other concentrations here and loadings. So that leaves us with the following equation, Rx times V. This can be set to be equal to QWXR plus, and QE is equal to Q minus QW, Q minus QW times XE in the effluent. All right, so then this can be algebraically manipulated, as we're going to see in a little bit. However, what we want to introduce here is the concept of the solids retention time. And solids retention time is equal to V times X, which is the volume times the concentration in the mixed liquor in the aeration basin, divided by the sum of the loadings that are leaving the system. So that would be Q minus QW XE plus QWXR. So the solids retention time is equal to the amount of biomass in the aeration tank, V times X. That gives us a mass of suspended solids. We use suspended solids to measure biomass. So mass of suspended solids, and divide that by these terms below, which are the flow rate leaving the system multiplied by the concentration leaving the system. That gives us a mass of volatile suspended solids per unit time, plus what's leaving in the sludge, same thing, a mass of volatile suspended solids per unit time. All right, so here we've got mass of volatile suspended solids, and on the denominator we've got mass of volatile suspended solids per time, usually days. So the mass cancel out, and what we have is days gets moved to the top. So that's the solids retention time in days. All right, so again, we utilize volatile suspended solids as a surrogate measurement for the biomass in this system, and we use the term X to denote biomass. All right, so this is the definition of the solids retention time. If we take the inverse of that, just an algebraic manipulation, we get 1 over SRT is equal to Q minus QW times XE plus QW XR divided by V times X. That is equal to V times Rx divided by Vx, because we know that this numerator here is equal to the volume times the net growth rate. So here the V's cancel out, and what we're left with is the specific growth rate, Rx divided by X, which is also, we use the term mu net, the net specific growth rate. All right, so this is an important connection here, that 1 over the solids retention time is equal to the mu net. All right, let's practice our knowledge of mass balance, keeping in mind that we want to think about this mathematically in terms of accumulation equal to inflow minus outflow plus net growth. All right, and so you're going to first do the mass balance for the boundary shown here on the bottom right. Complete the mass balance with respect to X for biomass, and then try to complete it with respect to S for an activated sludge system with recycle, where S is the substrate. We could say this is BOD. X is the biomass, and like I said, we usually use VSS. In some cases, people use TSS, but it's a little bit better usually to use VSS. For substrate, also sometimes we use COD. So these are approximate modeling approaches, and you'll see in different textbooks, you'll see some cases where BOD is used, some cases where biodegradable COD is used. Same with X, you'll see some cases where TSS is used and some cases where VSS is used. All right, so you're going to do this with this mass balance with respect to X and S. Q is the flow rate, RSU is the substrate utilization rate, R net is the net microbial growth rate, and V is the volume of the aeration tank. All right, so this example problem is to construct the mass balance of this system with respect to X and also with respect to S, the substrate. So you see this mass balance is set up very similarly to the way that we saw in the previous example problem, with the one exception that we're also including the primary clarifier inside the boundary here. And because of that, we are removing sludge from that primary clarifier at a flow rate Q sub PS, we'll call it. And it has a concentration of volatile suspended solids, XPS, and also has a substrate concentration, SPS. Now, again, let's start with the mass balance with respect to X. So again, in the previous example, we saw we ignored X naught because it's relatively small compared to the volatile suspended solids in the aeration tank and also in the sludge. So we can ignore that term, and that's going to be the case here as well. Assuming that X naught is negligible, we can also assume that XPS is also negligible in terms of the mass loading. So with those two assumptions in place, this is going to look very similar to the way it did in the previous example, with the one difference here is that the flow rate leaving the system is actually equal to Q minus QW minus Q of the primary sludge, to be accurate. So we want to take the rate of accumulation, which mathematically is V times dx over dt, and we assume that to be equal to 0 under steady state. And that's equal to what's coming into the system, in our case negligible, minus what's leaving the system. So this part we can consider negligible. However, we've still got the QW XR, and we've got Q minus QW minus QPS times XE. And then we need to add the rate of accumulation, or sorry, the growth rate, which is R sub x times V. So if we rearrange and simplify this equation, it looks very similar to the way it did before. Rx times V is equal to QW XR plus Q minus QW minus QPS times XE. All right, so that's with respect to X. Now let's do the same example, but with respect to substrate, which we usually use COD or BOD as a measure of substrate concentration. All right, so same mass balance, same concept. We have V times ds over dt, assumed to be 0 under steady state. And that's equal to what's coming into the system, so Q S naught minus what's leaving the system. So we have Q of the primary sludge times S of the primary sludge minus QWS minus Q minus QW minus QPS times S. And the reason why we have S substrate concentration as the same in the aeration tank and in that liquid effluent and in the sludge effluent is that S is being reduced from the influent to the effluent of the aeration tank. And if we're assuming complete mixing conditions, as indicated by the symbol there, complete mix inside the aeration tank, then the substrate concentration is uniform throughout the entire reactor, and it's equal to the effluent concentration. All right, so if the effluent concentration is S, and you have liquid-solid separation here, it's really not affecting the concentration of remaining substrate so much. So we can call that equal to S at all points in our mass balance. So now the only term we have left to add here is the rate of change. All right, so that's going to be equal to plus the rate of substrate utilization, S sub U, R sub SU, multiplied by the volume. All right, and that can be mathematically arranged as we saw before. For example, QS naught plus RSUV is equal to QPS SPS plus QWS plus Q minus QW minus QPS times S. All right, so there's the mass balance at steady state with respect to X and with respect to S. All right, let's do another example problem. Same system, however, this time we're going to draw the boundary in a different location. Now the boundary is drawn only around the secondary clarifier. Therefore, for this mass balance, what's coming into the system is coming from the aeration tank, right? So it's going to have the X. We're going to do this mass balance with respect to X. It's going to have the high concentration of mixed liquor, high concentration of biomass from the aeration tank because they grew, the microbes grew in that aeration tank. So you've got a high X value coming in, and you've got the X in the return activated sludge leaving this boundary. You've also got the X in the wasted sludge leaving this boundary. And you've got the X in the effluent leaving this boundary. All right, so in this problem, we have the same system as the last time. However, we're drawing our mass balance differently, right? Because we're only looking at the secondary clarifier here. All right, so otherwise, the same approach applies. We're still using mass balance. We have our boundary. The general mass balance formula, accumulation equals mass flow in minus mass flow out plus growth. That still applies. However, what's coming into our system is different than last time. So in particular, we've got the same effluents. We've got Q out still being equal to Q minus QW minus QPS. XE we can use for the VSS concentration in the liquid effluent. We have XR, which is the VSS concentration in the return and waste cycle. QW and QR to refer to the return flow rate of of return sludge, and QW for the flow rate of wasted sludge. However, the Q coming into the secondary clarifier is different, and we need to figure out how to represent it mathematically. So if we look at our overall system here, right, we've got Q coming in. What we're interested in right here is this flow rate between the aeration tank and the secondary clarifier. So if we follow Q throughout the system, coming in, we just call it Q. Leaving in the liquid effluent of this primary clarifier, it's really Q minus QPS. So at this point right here, it's Q minus QPS. And then we're adding back the flow rate of the return activated sludge. So at this point, right after that return line gets added, the flow rate is Q minus QPS plus QR. And as it goes through the aeration tank, there's no other outlets, so we can still use that as the same flow rate leaving the aeration tank, which is what's coming into the secondary clarifier. So Q in, which is labeled here, it's equal to Q minus QPS plus Q sub R. So now we set up our mass balance the same way as we have in the past. So we're doing this with respect to X, V dx over dt is equal to 0 at steady state. And that's equal to what's coming in. So Q minus QPS plus QR multiplied by X. Nothing else coming into our boundary, but we have 3 points where we have a flow leaving the boundary. So that's, first one is minus QR XR. Second one is minus QW XR. Then we have the effluent minus, this is in parentheses, Q minus QW minus QR, or sorry, QPS. Q minus W minus QPS multiplied by XE. And then the growth rate in here, this has a volume. We can assume that the growth rate in the secondary clarifier is negligible. This is not a reactor where we are feeding the wastewater with oxygen in order to promote the growth of microbes. We're just letting the biomass settle to the bottom. So we can assume that growth is negligible in this reactor. All right, so that's our mass balance. Of course, we can manipulate that algebraically and arrange it to solve for different terms within the mass balance. All right, so going back to one of the earlier mass balances that we saw, our equation is dx over dv times v is equal to q x naught minus qw times xe minus qwxr plus rxv. If we assume steady state in this system and we assume that the concentration of microbes coming in the raw wastewater and influent here is going to be, or the primary treated wastewater, we assume that that's negligible compared to what's growing in the aeration tank, then we can simplify this equation to the following form here below. Q minus QWXE plus QWXR is equal to RX times V. So recall from our previous equations that we saw in the previous slides, 1 over the solids retention time is equal to Rx over X, which is also equal to this right here. And we also know that Rx over X is equal to Y times the substrate utilization rate over X minus B, which is equal to Y times Ks over K sub S plus S, which is the Minod term, minus B. All right, so we've got these two equations here where which are both equal to Rx over X. And just to note, in this system, the way that it's configured, we've got sludge being wasted. Sometimes that's referred to as X sub W for waste sludge. And sometimes it's referred to as XR because it's really the same concentration of the return activated sludge. All right, so XR being equal to XW. With these two equations right here and understanding that these two are equal to each other, we can simplify this to show that 1 over the solids retention time is equal to Y times the substrate utilization rate over X minus B. Okay, and in some cases, this equation right here, we also know that it's equal to Q minus QW times XE, which is basically what's leaving the system in the liquid effluent, plus what's leaving the system in the sludge, QWXR, divided by VX. All right, in some cases, this actually might be ignored, this term right here, because the suspended solids concentration in the secondary effluent is usually quite low compared to what's in the sludge. So depending on what assumptions you make, you may or may not ignore this term right here. But either way, we've got this equation, which we've derived. We are defining the substrate utilization rate. We can define it as the flow rate times what gets consumed from the BOD or COD. So S0 minus S times the flow rate. That gives us the loading that's consumed, right? The mass of BOD or COD per unit time that's consumed in the reaction. And that's divided by the volume. If we divided that by the volume, this is the substrate utilization rate. We can then substitute this term into the equation above, and that gives us 1 over SRT is equal to YQ times S0 minus S divided by XV, the whole thing minus B, the decay rate coefficient. All right, recall that the hydraulic retention time is equal to V over Q. So this V on the bottom here and Q up on the top, we can utilize this knowledge of V over Q equals to HRT to substitute in. And with some algebraic rearrangement, we can get the equation in the following form. X equal to SRT over HRT multiplied by this term right here, Y times S0 minus S divided by 1 plus B times the solids retention time. This equation is one that you'll see in the FE manual when you take the FE exam or the PE exam. And it is one of the most crucial equations that's used for representing and modeling suspended growth treatment processes. Okay, so now from the substrate mass balance, again, the mass balance on S, on the term S, we have ds over dv times v is equal to q times S naught minus q times S plus the substrate utilization rate times v. Assuming steady state and substituting for the substrate utilization rate, recall that that's equal to kxs divided by ks plus s. We get the following equation. S0 minus S is equal to V over Q times KXS divided by KS plus S. All right, if we take our equation that we derived for the biomass up here and we substitute it in for X in this equation down here, we get the following equation shown below. All right, some simplification and algebraic manipulation will bring us to the simplified version shown here. This is the second of the two primary equations utilized for modeling suspended growth biological treatment processes. This is the substrate equation. The first one is the biomass equation. The second one is the substrate equation. So S is equal to Ks times 1 plus B times SRT divided by the SRT times the maximum specific growth rate minus B, and that whole thing minus 1 in the denominator. All right, and remember that this maximum specific growth rate can be related to this K value right here from our previous slide. So here you can see that both the biomass concentration in the reactor and the substrate concentration leaving the reactor, which is the effluent BOD or the effluent COD, they're both related to the solids retention time. And the biomass is also related to the hydraulic retention time. But they're both related to the solids retention time, meaning that solids retention time is a key design parameter for us to balance our biomass concentration in the mixed liquor and also to optimize our effluent substrate concentration, which basically sets the efficiency of our activated sludge system. Because we can calculate the percent removal of BOD or COD by utilizing S sub 0 and the value S that's leaving the reactor. All right, so these two equations, very important to have at hand when completing the example problems that we'll be doing. So a little bit more about the solids retention time. This is also known as the sludge age or the mean cell residence time, and it represents the average amount of time that sludge or biomass has remained in the system. All right, for BOD removal only, typical SRT values may range from 3 to 5 days, depending on the temperature of the mixed liquor. So at like 18 to 25 degrees, SRT value close to 3 days is typical, but you'll see values as low as 1 day used in some systems, especially when the operator does not want nitrification to take place. At colder temperatures, you might see SRT values more like 5 or 6 days. All right, so just again, a little bit of background here that if we want nitrification to happen, we will need longer solids retention times because we not only need the microbes to oxidize the organic matter, we also want them to oxidize the ammonia, and those microbes work a little bit slower. We're going to get into a little bit more detail about that in a few minutes. But if we don't want nitrification to take place, we can use lower SRT values, and that will result in the conversion of organic matter to CO2, but not necessarily the conversion of ammonia nitrogen to nitrate. All right, so depending on our goals, we're going to set an SRT value for our system. This is the most critical design parameter, as I mentioned, for process design because it affects the process performance, it affects the volume of the aeration tank, it affects the sludge production rate, and the oxygen requirements, all of which are related to cost of operating the system. Some other parameters that we can keep in mind are the sludge return rate. This is the fraction of sludge that's recycled in the system. So it's the flow rate of the recycled sludge divided by the overall flow rate. It's also equal to 1 minus the ratio of HRT to SRT divided by the ratio of X sub R divided by X minus 1. All right, so you can relate these terms to the flow rates of return sludge. We also have the organic volumetric loading rate. This is the amount of BOD or COD that's applied to the aeration tank volume per day. So that's the flow rate multiplied by the substrate concentration coming into the aeration tank, and that's divided by the volume of the tank itself. The food to microorganism ratio is defined as the rate of BOD or COD, or the rate of substrate that's applied per unit mass of mixed liquor. So typical values are 0.04 grams of BOD per gram of VSS per day. That would be for an extended aeration system, or 1 gram of BOD per gram of VSS per day for high rate processes. All right, so it's the total applied substrate divided by the total microbial biomass, and it's calculated as the flow rate times the substrate concentration divided by V times X. Very similar to the organic volumetric loading rate, but we utilize the biomass concentration in the denominator in order to normalize it for the microbial biomass, not just the volume. The solids retention time, again, is the average time the sludge remained in the system. And just to not forget that the solids retention time, as well as all of the mass balance equations that we derived previously, those are dependent on the process configuration. So for this typical configuration that we've been looking at so far, where the mixed liquor suspended solids or the sludge is wasted from the return line, we know that SRT is equal to Vx over QW plus QE. However, if the sludge is wasted from the aeration tank, as shown in this diagram here, then SRT is equal to V divided by QW. And we can demonstrate this using mass balance. For an Mbr system, a membrane bioreactor system, where we've got a return line and we've got a membrane, the permeate is discharged, as well as the sludge, which is wasted from the return line, we can represent the SRT using the following equation, where VA is the volume of the aeration basin and VM is the volume of the membrane chamber. All right, for organic matter removal, the effluent substrate concentration, BOD, or biodegradable soluble COD, is calculated using the following formula, which again was derived in the previous slide as one of those master equations for the activated sludge process. All right, the removal efficiency of BOD or biodegradable soluble COD can also be related to the F to M ratio, the food to microorganism ratio. It can be related to the SRT, the true microbial yield, and the decay rate, as shown here. So the efficiency of removal of the substrate is equal to 1 over SRT plus B times 1 over Y times F to M ratio. We can also utilize these terms to estimate sludge production, and this is very important for several of the example problems that we'll be doing in a few minutes. So sludge production can be estimated based on a detailed and complete characterization of the wastewater to be treated. So if we know these terms like flow rate and some assumed values for yield and the decay rate, as well as our SRT that we're using for design, our influent and effluent substrate concentration, and some other terms here, which I'll go into in a second, we can estimate the rate of sludge that's going to be produced in the system, which helps us plan how big our sludge management processes need to be sized for. All right, so this first term in the equation represents the sludge that corresponds to heterotrophic biomass. Heterotrophs are those microorganisms that are degrading carbon compounds to CO2. The second term here represents cell debris. So these are the decayed microorganisms after they're no longer active and their cellular biomass is starting to be consumed in the system, but there's some that will remain. It's not degraded, it's not reused in the process, and that remains as cell debris, which is this term right here. The C term is the nitrifying biomass. This would only be relevant in a system where nitrification is taking place. Otherwise, you can just omit this term from the equation. And the final term is a small percentage of the biomass, which is non-biodegradable. All right, in some cases you might see this ignored because it's relatively small. This is the estimated concentration of volatile suspended solids. If we wanted to estimate the total suspended solids concentration produced per day, then we would just divide each of these terms, A, B, and C, divide that by 0.85 based on the fixed proportion of solids that is typical for these systems. Then we'll still add the non-biodegradable suspended solids here, term D, and we'll also add this term E, which is the influent inert total suspended solids. All right, so the design process here consists of a few steps. The first step is to select an appropriate mixed liquor suspended solids concentration. Some typical values for TSS to choose for a design purpose might be in the range of like 1,200 to 4,000 milligrams per liter. Then we would use the following equation to calculate an estimated volume that we can use for our reactor. Using this P sub x, which is the total suspended solids production rate, multiplied by our SRT value that we're using for design, divided by the TSS concentration in the reactor. And then we would calculate the hydraulic retention time, which of course is V over Q. And with that, we can specify some of the main parameters for our activated sludge system. This table right here comes from the Metcalfe and Eddy book, and it shows just a summary of typical operational parameters, ranges you might find for aeration processes, activated sludge processes, conventional activated sludge, step aeration processes, extended aeration, and high purity oxygen processes. So you have this typical range that you can use when you're working on a design problem.